Grade 12 Doppler's effect, question 16. The siren of a police car, which is traveling at a constant speed along a straight horizontal road, emits sound waves of constant frequency. Detector P is placed inside the police car and detector Q is placed next to the road at a certain distance away from the car. The two detectors record the changes in the air pressure readings caused by the sound waves emitted by the siren as a function of time. So what is happening here is that whenever sound travels through air, it causes the air molecules to compress. So they were recording the pressure of air as it changes when sound is traveling through it. So the first graph is the graph obtained from the readings detected by detector P. And the second graph is the graph of the air pressure showing the readings that were detected by detector Q. Now, just by looking at the two diagrams, we can tell that this graph has a higher frequency because the waves are sort of compressed, and this one, the waves are larger. We can also tell by how long or how short each cycle of a wave takes. This one takes only 17 times 10 to the power negative 4 seconds, and this one takes 18 times 10 to the power negative 4 seconds. So that's the period of each wave, like how long each wave takes to complete a single cycle. Now the first question, 16.1, says different patterns are shown above for the same sound wave emitted by the siren. What phenomenon is illustrated by the two detectors showing the different patterns? Doppler's effect. 16.2 says use the graphs and give a reason why it can be confirmed that the police car is moving away from detector Q. As we have mentioned, frequency detected by detector P is higher than the frequency detected by detector Q. According to Doppler's effect, when a sound source is moving away from the detector records a lower frequency. So we can use Doppler's effect to deduce or to confirm that the police car is moving away from detector Q, because we know if a sound source is moving away from our detector, then our detector will register a lower frequency. So we say detector Q has a lower frequency than detector P, or detector Q has longer, because period is time, period, than detector P. And now question 16.3, calculate the frequency of the sound waves recorded by detector P. Now we don't know the frequency of these graphs, we only know the period, right? We are going to use this formula. It says T is equal to 1 over F. Now T here is for period, F is for frequency. Manipulate the formula by making F the subject. We are going to have frequency times period is equal to 1, because this is going to cancel. Then we can divide by period, frequency is equal to 1 over period. Now we need to look at the graph of P to figure out its period. Now as I've said, it is from 0 to 17 times 10 to the power negative 4 seconds. Or the other way to look at it is looking from this point over here. This is also one complete wave, but you're gonna have to say 25.5 minus 8.5. That's a lot of work, so we can just say 17 times 10 to the power negative 4. So the period for detector P is 17 times 10 to the power negative 4. We plug that into our calculator, we get 588.24 Hertz. And we are told that detector P is placed inside the police car, meaning detector P detects the frequency of the sound source because the car is emitting the sound. Therefore, the frequency detected by P is frequency of the sound source. Use the information in the graphs to calculate the speed of the police car. Take the speed of sound in the air as 340 meters per second. Now we also going to have to calculate the frequency detected by detector Q. Period is equal to 1 over frequency. Now what is the period for detector Q? It is 18 times 10 to the power negative 4 seconds. Don't forget this, guys. So when we plug that into our calculator, we get 555,56 hertz. Now this is frequency detected by the listener because detector Q is not inside the police car. So now we have frequency of the sound source and frequency detected by the listener or the observer. Now we're going to use our Doppler's effect formula, which is frequency of detected by the listener is equal to V plus or minus VL divided by V plus or minus Vs times frequency of the sound source. Now they told us that the police car is moving away from detector Q. Now what I normally do is I use the T and F method to figure out the signs. Now when they say the sound source is moving towards the listener, or the listener is moving towards the sound source, the sign on the numerator is going to be a plus because they say towards, and the sign on the numerator is going to be a minus. Now if they say the sound source is moving from the detector, or the detector is moving from the sound source, then the sign on our numerator is going to be a minus, and the sign on our denominator is going to be a plus. It's as easy as that. So in our scenario, they said that the police car, which is the sound source, is moving away from detector Q, and detector Q is our detector, is our listener. Our police car is moving away from our listener, so we're going to use this equation, away from our listener. Now they told us that the speed of sound in air is 340, and the velocity of our listener is 0 because he or she is just standing there, and we are looking for velocity of the sound source, which is our police car, times 588,24 hertz. So mathematically, this is going to multiply with this, and this is going to multiply with this. Now when you distribute, it's going to look like this: 200,001,6. Now we're going to move this to the other side and be left with 555,56 Vs is equal to 200,001,6 minus 188,890,4. We get 11,111,2 divided by 555,56 divided by 555,56. Now the velocity of the sound source is equal to 20 meters per second. Thank you for watching.